Welcome to In 5 Minutes. We take problem on shear stress in circular section. A problem statement is deduce the relation for the maximum and mean shear stress across a section for circular cross section. So in this problem we have to determine relation between your tau max and tau mean. Now consider a circular cross section whose diameter is d and radius is r, whereas O is the center of the circular cross section. We have shown the horizontal centroidal x-axis, which will also be your neutral axis for the cross section. Let us take a point P on this layer and we determine the shear stress on this layer. Now if we consider the shaded area of the part of the cross section which is above the layer, we see that the depth of this layer will be given by d by 2 minus y, where d is your diameter or total depth of the cross section. Now we know that the shear stress on this layer will be given by the formula tau is equal to Fa y bar upon Ib, where your F, I and B are the shear force acting on the cross section, I is the moment of inertia of the whole cross section, whereas B is the width of the layer at which we have to determine the shear stress. Now this Ay bar is the first moment of the shaded area about the neutral axis. Now we see, since this shaded area is asymmetrical about the neutral axis, to determine the first moment of this shaded area we have, let us consider a small elemental area within this shaded part of the cross section which is parallel to the centroidal x-axis or your neutral axis. The width of the elemental strip is b, whereas its depth is dy. Let us do small construction within this cross section where we see that the width of the layer will be given by AC and it will be equal to 2 times of AB or 2 times of BC. So now the area of elemental strip will be given as dA equal to B into dy. So we can write dA is equal to, your B could be written as 2 times of AB into dy. Now if we consider the triangle ABO, we have AB square plus BO square is equal to AO square. So we have AB square is equal to AO square, which is nothing but R square, radius of the cross section, minus BO square, which is nothing but y. So we have y square. So your AB is equal to square root of R square minus y square. So upon substituting this value in this equation, we have dA is equal to 2 times of square root of R square minus y square multiplied by dy. Now the moment of this elemental strip area about neutral axis, if we consider this elemental strip at the same layer at which we have to determine the shear stress, then the moment of this small elemental area about the neutral axis will be given as y into dA. This is by considering this small elemental area on or above this layer. So upon substituting the value of dA, we have y into 2 into square root of r square minus y square multiplied by dy. So this is equal to 2y into square root of r square minus y square into dy. The moment of this whole shaded area, the moment of this whole shaded area above the neutral axis could be obtained by integrating the above equation between the limits y to d by 2. That means from this layer up to the extreme top part of the cross section, which is at a distance d by 2 from the neutral axis. So we have Ay bar, which is nothing but the first moment of this shaded area above the neutral axis, equal to integral of y to d by 2, which is nothing but radius r, into 2y square root of r square minus y square into dy. Now for integration, we write Ay bar as minus of integral y to r minus of 2y into square root of r square minus y square by dy. So we simply introduce this 2 minus signs over here. Now minus 2y is the differential of square root of r square minus y square. So by the property of integration, we have Ay bar is equal to minus of the integral of simple this term, that is square root of r square minus y square. So we have r square minus y square into power 3 by 2 upon 3 by 2. Now since this square root of r square minus y square is r square minus y square to the power 1 by 2, when we integrate it we get r square minus y square to the power 3 by 2 and 3 by 2 into denominator. Within the limits r to y. Now this is equal to minus of 2 by 3 r square minus r square to the power 3 by 2 minus r square minus y square to the power 3 by 2. This we obtain by applying the limits. So we have ay bar is equal to, this minus sign and this minus sign gets cancelled. So 2 by 3 r square minus y square to the power 3 by 2.